Welcome back to section 7 of chapter 4. In this section, we're going to be introduced to the inverse trig functions. We're going to see what the functions look like as graphs. We're going to see the domain and the range. And we're going to get a little bit of the application, but really the application comes in the next section more than anything else, because these are used to solve problems involving trig. So, let's take a look at our learning targets. Find the exact values of inverse trig functions. Use a calculator to find approximate values of inverse trig functions. That's pretty easy when you just hit a couple buttons in your calculator and there you go. Analyze graphs of inverse trig functions. Evaluate composite functions involving inverse trigonometric functions. Those are the ones that I really like because you can't just use a calculator for them. You actually have to know what you're doing. So, I mean, that's not a hint on what's going to be on the test and quiz and stuff like that, but that's what I really like. And using transformations to describe graphs of inverse trig functions. So, first of all, let's start out with inverse sine. So the inverse is just like any other inverse. The graph of it reflects across the line y equals x. We switch the x and the y variables. So if we just graphed this, the red one is y equals sine x. The blue one is x equals sine y. It's the inverse of the sine graph. Now, this is a little bit problematic, especially since I called it an inverse sine function. It's being that sine is periodic, it has that wave. When we take the inverse, it's definitely not a function. It does not pass the vertical line test. And so because of that, we're going to cut it down. We're going to restrict it. So for the sine graph, we just go from the bottom to the top. And then we flip that. So it only goes from there to there, or there. So this first one here, this is the part of the sine graph that we use. So it would have to pass a horizontal line test. So we have to get the whole span of the range. So we go from the bottom up to the top, a minimum to a maximum. And then we can flip that over the line y equals x. Well, the thing about sine is from that minimum to the maximum, it almost looks like y equals x. So really the difference here between the sine and the inverse sine is you can tell the end of the sine curves down, the end of the inverse sine curves up just a little bit. Other than that, they look very, very similar. And so what is this inverse sine? This inverse sine is, if we're looking at our triangle, we have an angle, we have the opposite, we have the hypotenuse. We know that the sine of the angle equals the opposite over the hypotenuse. The inverse sine switches those. The sine takes the angle and makes the ratio. The inverse sine of the ratio gives us the angle. That's a theta. I'm going to redo. That was a sad, sad theta. There we go. So the inverse sine of the ratio gets us back to the angle. It undoes what the sine does. It flips it backwards. One of the notations uses the -1, which is the notation for the inverse. On your calculators, the second sine button, like you push second and then you push sine on basically every calculator out there that has a sine button, it's sine -1. That's inverse sine. It's not the reciprocal. That's not the cosecant. It's the inverse. Cosecant is reciprocal. The inverse is the sine -1. This is also called the arc sine, and it can be written ARC sine of x. I don't want to put theta because you don't put an angle into the arc sine. You get an angle out of the arc sine. So the inverse sine, both notations are perfectly fine. When I'm doing things, I generally go with the to the -1 notation. That's my preference, my habit. That's what I do. When I'm writing things out and I need both, I usually have to go back and change some to the arc sine. So what you use doesn't really matter, but you do need to be able to recognize both of them and that they both mean the same thing. So um, some stuff about it. So unique angle y is in the interval -pi/2 to pi/2, such that sine of y equals x is the inverse sine or arc sine of x, denoted inverse sine x or arc sine, so it's both the things. The domain of the arc sine is -1 to 1 because the range of the sine was -1 to 1, and then the range is -pi/2 to pi/2 because that's the domain from the minimum to the maximum. And so notice that the arc sine is very, very limited in both the domain and the range, even though the sine keeps going. And so that's going to not cause problems, but we're going to see some stuff with that's I want to say a little bit weird. It's not weird, but just something to be aware of. Inverse cosine function. It's basically the same. So we can look at the cosine graph and then the inverse of the cosine graph. Now, the cosine goes from the minimum to the maximum all in the negatives, from -pi to 0. And as opposed to having everything be in the negatives here, we take everything in the positive. So we're going to start from 0 and go to pi, which when you flip that, when you do the inverse, starts from 0 and goes to pi. So looks kind of like that. The cosine, it means the same. We have if cosine of the angle equals the adjacent over the hypotenuse, that means the arc cosine or the inverse cosine of the adjacent over the hypotenuse, not an angle, is going to be back to the angle, as long as the angle is in between 0 and pi. It will give us an angle in between 0 and pi. Remember, there are two things around the circle that give cosine a certain value. The arc cosine and the arc sine will only give us the smaller of those two things. It gives us the one in between either 0 and pi for cosine, or -pi/2 and +pi/2 for sine. That's that little bit of weirdness. It gives us something that might not be the same thing. If we start out with a bigger angle, it'll give us a smaller one. And then this could also be written as arc cosine of x. Arc cosine with the two C's is a little bit weird. You don't see it very much, but arc cosecant is even weirder looking. We generally do the arc trig for sine, cosine, tangent. If you have one of the others, you wouldn't. You would use sine, cosine, or tangent. Generally speaking, they come from problems, and you'd set up a problem using those as opposed to your cosecant, secant, and cotangents. So the inverse cosine, same deal, except that the Domain is from -1 to 1, and the range is from 0 to pi. So the domain's the same because the range is the same for sine cosine. But now the range is 0 to pi instead of -pi/2 to +pi/2. The last of the inverse functions, we have inverse tangent. Now, remember the tangent repeats, and it's not that wave, it's something else. And then the inverse flips it. I have to say, this graph where we have both the tangent and its inverse on the same graph, it looks kind of cool. Like it looks like the screen is warped. It's like an optical illusion type deal here. And so this would be all of them, but just like with the rest, we have to limit it because of that repetition. We only want one repetition. Tangent has a fantastic place to stop though, because it has these vertical asymptotes, which would turn into horizontal asymptotes. And so we use only one of the repetitions. So, and the tangent is the same. We have tangent of theta would equal the opposite over the adjacent, which means that the inverse tangent of theta of the opposite over the adjacent, so used to doing trig of theta, opposite over adjacent, gets us back to theta. So, and then we can also write it as arc tangent of x would equal the angle. Our definition here we have the domain is from -infinity to infinity because it has those horizontal asymptotes. So the end behavior, as the inverse tangent is going to -infinity, it has an asymptote. It's going to -pi/2. And as it's going to infinity, it's going to +pi/2. So we have those asymptotes, and then the range is in between -pi/2 and +pi/2, but notice it's non-inclusive here because it won't actually get to those numbers because it's asymptotic there. Some evaluating. You'll have to evaluate without a calculator, and it just goes backwards. It goes back to that unit circle that we were looking at a few weeks ago and every day since. So now we're looking at the ratios. We're trying to find the angle. So we have inverse sine of 1/2. The question here is what angle gives us a sine of 1/2? And that would be 30 degrees or pi/6. The angle pi/6 has a sine of 1/2, that y value of 1/2. How about negative √3/2? Well, it's going to be negative, so it's backwards. √3/2 is going to be pi/3, so this will be negative pi/3. Is the inverse sine there? Inverse sine of pi/2. Well, that's weird. We don't usually have, like, pi/2 is an angle. I mean, we could do an inverse sine of it, except that the inverse sine, the range of inverse sine, or the domain of inverse sine is only from -1 to +1. Pi/2 is bigger than that. So this doesn't exist. You can't do that one. Now, if it was inverse sine of 0.2, yes, you could do that. It's not one that we would know though. You would need to use a calculator for that one. How about the inverse sine of the sine of pi over 9? The inverse sine of the sine. Wait, don't inverses and the non-inverse cancel itself out? Yeah, generally speaking, yes. That's just pi over 9. Inverse sine of 5 pi over 6. Well, that's kind of silly. Isn't that just kind of like what I just did? Kind of yes and no. Yes, it cancels itself out, but the range of the inverse sine only goes from negative pi over 2 to positive pi over 2. 5 pi over 6 isn't in there. We're going to get not a coterminal angle. We're going to get the other angle, the smaller angle that has the same sine value. So if we think about our unit circle on this one, 5 pi over 6 is over here. So we need the angle in this half of a circle that has the same height. That's that one. It's just pi over 6. Or you could go sine of 5 pi over 6 is 1/2. And then we know the inverse sine of 1/2 is pi over 6 from up there. So there's a few ways of doing that. Generally speaking, a composite with its inverse cancels itself out as long as it's in the range and or domain of the inverse there. Composing some trig functions with arcsine. We're just doing it with arcsine. It could be with any of them. So we saw sine of inverse sine of x. So it was the other way around, but same idea, that those two things are just going to cancel each other out, and it's x. What about the rest of them? Well, it's not just x. But for this, we can draw a picture. Anytime we work with triangles, I would draw a picture. So sine of x, let's say sine of x equals y. Well, that y is the angle because the sine of the ratio, and this ratio is x over 1, is opposite over hypotenuse. If you do 1 squared minus x squared, it'll equal that other side squared. Square root, this side will be the square root of 1 minus x squared. And note that is not 1 minus x. Don't be that guy. You can't just square root each thing individually. It's 1 minus x squared because it's 1 squared minus x squared, and then square root. Well, now, so not sine of x, the inverse sine of x equals y, so it equals that angle. So any of these could be written as y now. We have the different pieces, we just plug them in. So cosine is going to be adjacent over hypotenuse. We have root 1 minus x squared over 1. Tangent, opposite over adjacent, x over root 1 minus x squared. If you really feel the need, you could multiply both sides by the root to get x times root 1 minus x squared over 1 minus x squared. You could do that, or you could leave it with the root in the denominator for now. Cosecant, these are all the reciprocals. So if sine was x, cosecant will be 1 over x. The secant will be 1 over that square root. Or you multiply both by top and the bottom, and you get the square root of 1 minus x squared over 1 minus x squared. And then cotangent we would flip, so we'd have the square root of 1 minus x squared over x. So you can do a composite by make a triangle, label the triangle, and then from there you have all of the same trig functions that you have had. And then finally, an application here. We have the bottom of a 20-foot replay screen at Dodger Stadium is 45 feet above the playing field. As you move away from the wall, the angle formed by the screen at your eye changes. There's a distance from the wall at which the angle is greatest. What is this distance? So, again, draw a picture. We have a triangle. And that triangle, we have this 20-foot display. So that's 20, and it's 45 feet above the playing field, so 45. Let's see. So we're looking at distance from the wall. We'll call that x. And then the angle we're looking for is this angle. That angle is going to be the big angle minus the smaller angle. So let's say theta equals theta 1 minus theta 2. So, so the angle we're looking at is theta 1 minus theta 2. To find those, we have an opposite side, we have an adjacent side. That's going to be tangent. So theta 1 is going to be the inverse tangent, or actually, let's start out the other side of that one. Tangent of theta 1 is going to be the opposite, which is 20 plus 45, so 65 over x. Now we can do the inverse tangent of both sides. Theta 1 equals inverse tangent of 65 over x. And then same thing with theta 2. Tangent of theta 2 is going to be 45 over x, which means theta 2 equals the inverse tangent of 45 over x. Now, we're looking for theta 1 minus theta 2, so that angle of our eyes is going to be theta 1, which is inverse tangent of 65 over x, minus theta 2, which is inverse tangent of 45 over x. All right, well, now we have an equation. So we can solve this. How are we going to solve this, though? That's pretty ugly. And I agree. That is pretty ugly because you can't combine those. At least not yet or pleasantly. What other tools do we have? We could graph this. So we graph it, and it starts out the angle's really small because as you're looking up at it, the angle that you can even see it drops. And then it gets big, and then it goes down. And then with whatever we graphed on, whether it's Desmos, tells us maximums and minimums, it could be graphing calculator, it could be anything, but we just use those graphing features to find the maximum, and it turns out to be about 54 feet. Will give you the maximum angle that you have to look in, like to see the jumbotron. So that is an example of an application. Again, we'll be doing a lot more applications next time. But when you're doing applications, draw a picture of your triangle, figure out what you need to find. it's very possible that you will use tangent a lot in your applications. It is used a lot in applications. So um, I will see you in class though. Until then, keep working problems, keep asking questions, and as always, happy mathing.